The question is, could you derive equations for principal stresses and maximum shear stresses for the 2D stress problem? Let's start with the stress transformation equations, and here's a summary of them. We obtain x prime axis by rotating the x-axis through an angle of theta in the counterclockwise direction. The y prime axis is perpendicular to that, so it's a little differential element drawn with respect to the x prime, y prime axes, showing the stresses acting on the faces of the differential element. Here's the equation for sigma x prime, and here's the equation for tau xy prime. There is, of course, another equation for sigma y prime, which we don't need at this point. And here are the same equations in a more compact form, which are a lot more convenient for the analysis we want to do here. So what we did here is we defined three parameters, sigma average, A, and B, as these, and then rewrote sigma x prime and sigma xy prime, tau xy prime, in terms of the three parameters. Here's a picture from another video illustrating the meaning of principal stresses and the maximum shear stresses. And here I have chosen a numerical example to achieve this. And this picture shows the 2D state of stress at a certain point. Sigma prime and tau prime are the stresses on the x prime plane, which is obtained by rotating the x-axis through an angle of theta in the counterclockwise direction. As I increase theta from 0, when theta becomes equal to 62 degrees, this is what happens. Shear stress becomes equal to 0, and the normal stress on that plane becomes the maximum possible for this point, and in this particular example, that maximum stress is 38 kilopascal. And if I rotate through another 45 degrees, the shear stress becomes maximum, and there is of course a normal stress, but the bottom line is the shear stress is the maximum possible for this point. And you rotate through another 45 degrees, the normal stress becomes the minimum possible for that point, and the shear stress again is 0. And when you rotate this through another 45 degrees, the shear stress assumes the maximum value one more time in magnitude, but the direction becomes opposite. In other words, over here we have the shear stress acting in the clockwise direction, whereas here the shear stress is acting in the counterclockwise direction. The normal stress over here is the same as the normal stress over there. These two normal stresses are called the principal stresses. One is the maximum possible and the other is the minimum possible. And also note that the shear stress on the planes where the principal stresses are acting are 0. And these are called the principal planes. And of course these are the maximum shear stresses. So we want to be able to predict these. We want to be able to predict the magnitudes and the directions. And we use calculus to achieve this. We know that the principal stresses represent the maximum and minimum normal stresses, right? And therefore the first derivative of sigma x prime with respect to theta must be 0 for these planes, right? So that gives us a basis for developing an equation for the principal stresses. And similarly, the shear stress is the maximum on these planes, and therefore the first derivative of tau xy prime with respect to theta must be 0 for these planes. Let's take the compact forms of the equations for further analysis. Here is the first derivative of sigma x prime. We set this to 0, and that gives us this equation for the angle theta at which this happens. So here we have tan 2 theta equals b over a, right? So if I were to draw a right triangle like this, and make the opposite side of this angle as b and the adjacent side as a, the hypotenuse will be a squared plus b squared, right? Let me also point out that the hypotenuse is not just a squared plus b squared square root. It could be plus or minus, right? In other words, there are two possible values for this. Alright, keeping that in mind, now we're going to substitute this angle into equation number 1. That will give us an expression for the principal stresses. So here it is, sigma x prime equals sigma average plus a times cosine 2 theta. So now we come back to this little triangle. Cosine 2 theta would be a over plus or minus square root of a squared plus b squared, right? And then plus b times sine 2 theta. Sine 2 theta would be b over plus or minus square root of a squared plus b squared. So that simplifies to this. So in the interest of keeping these equations as compact as possible, let me define one other parameter, r. r is the square root of a squared plus b squared. And then in terms of r, then the two values of the principal stresses we get out of this is sigma average plus or minus r. So I write this as sigma 1 comma 2 because there are two principal stresses in here. One goes with the plus sign, the other one goes with the minus sign. And the other thing we want to note here is that there are two angles in here. If tan 2 theta p equals b over a, then the trigonometric relations tell us that tan 2 theta p minus 180 will also be equal to b over a. So when we simplify this, we get a second angle for the direction of the principal stress. So let's call this as alpha p. And here is the relationship between alpha p and theta p that we got earlier. Another property of interest to us is the shear stress on the principal planes. To investigate this, I take the shear stress equation and substitute theta p into that equation. So here is the analysis. So the analysis leads to the conclusion that the shear stress on the principal planes are 0. We know there are two principal planes and the shear stresses on both of those planes are 0. So here's a little summary. We got two principal stresses, sigma 1 and sigma 2. Sigma 1 is sigma average plus r. Sigma 2 is sigma average minus r. And we got two angles, theta p and alpha p. But here's a little problem. We don't know which angle goes with what principal stress. So how do we establish that? Well, principal stresses are basically the minimum and maximum normal stresses, right? Minimum and maximum value of sigma x prime, right? So what we do is we take one of the two angles, either theta p or alpha p, and then substitute in this equation. Let's say we chose theta p, right? And sigma x prime works out to be equal to sigma 1. Then we know theta p goes with sigma 1, and the other angle alpha p goes with sigma 2. Otherwise, it's the other way around. That's it. Here is the corresponding analysis for the shear stress. Here is the shear stress equation. We take the first derivative of tau xy prime with respect to theta and set it to 0. That gives us this angle for the direction of the maximum shear stress. We substitute this back in the original equation for tau xy prime, and we get this expression for the maximum shear stress. Once again, we have two values which are plus or minus r, where r is this right here. Also, just as in the case of the analysis on principal stresses, if this is true, there's a second angle that is given by this equation. The second angle differs from the first angle by 90 degrees. So here are the two values for the maximum shear stresses, and here are the two values for the directions. Once again, we don't know which one goes with what. We have to use the same technique that we used in the case of the principal stresses to establish which of the two angles go with which of the principal stresses. Just as we investigated the shear stresses on the principal planes, it is of interest to know the normal stresses on the planes of maximum shear stresses. We follow the same approach. We take the equation for the normal stress and substitute theta s into that equation. So that leads to this value for sigma x prime. In other words, we get the same value of the normal stress on both planes of maximum shear, and the value is sigma average. So here's the overall summary of the equations for the principal stresses and the maximum shear stresses. Also note the following. We know tan 2 theta p equals b over a, right? So let me call that as m1. And similarly, we know tan 2 theta s equals minus a over b. Let me call that as m2. Now if I were to multiply m1 by m2, I get minus 1, right? You might recall, if this is true, then the two lines are perpendicular to each other, right? In other words, 2 theta p and 2 theta s differ by 90 degrees, or theta p and theta s differ by 45 degrees. Now see, what we discussed in the introduction makes sense. We proved that the two principal directions are perpendicular to each other, and that's what we found in this analysis, right? So this direction and this direction are perpendicular to each other. The two planes of maximum shear stresses are perpendicular to each other. This is one plane, this is the other plane. Both of them are at 90 degrees to each other. The planes containing the maximum and minimum principal stresses and the planes containing the maximum shear stresses differ by 45 degrees. So in other words, the angle in between these two lines is 45 degrees. The shear stresses on the principal planes are 0. The normal stresses on the planes of maximum shear stresses are equal to each other. So in this particular case, it's 20 kilopascal. And we proved that this value is supposed to be sigma average. Sigma average is sigma x plus sigma y divided by 2, right? So that will be 10 plus 30 over 2, which is 20. So that's how we got 20 over here.